Welcome to this explainer. Today, we're going to fundamentally shift how we think about the sounds around us. Most people just treat environmental noise as a daily annoyance, something you just have to live with. But in physics and acoustic engineering, it's a quantifiable health hazard. And here's the beautiful part. Because it can be quantified, it can actually be engineered away. So let's dive right in and examine the precise control measures we use to systematically neutralize noise pollution.
Here is our roadmap for today's explainer. 1. Measuring sound accurately. 2. The source-path-receiver model. 3. Controlling noise at source. 4. Blocking the transmission path. 5. Defending the receiver. And finally 6. Macro-level noise strategies.
Section 1. Measuring sound accurately. The diagnostic tool. As any veteran engineer will tell you, before we can alter an environment or implement a single control measure, we have to accurately measure the hazard. We need to find the equivalent sound pressure level, which is typically measured in decibels. A sound level meter achieves this incredibly elegantly. Basically, a microphone captures acoustic sound waves and transforms them directly into an electrical signal. That raw signal then passes through an internal electronic network that modifies and weights it, essentially translating raw physics into a meaningful, standardized metric. Finally, it communicates those actionable results to an analog or digital display. Getting this precise measurement is the absolute critical first step before the real acoustic engineering can begin.
Section 2. The source-path-receiver model, the core paradigm.
Right, so now that we have our measurements, let's introduce the foundational framework used by acoustic engineers all over the world. Every single noise problem, no matter how complex, follows this exact linear progression. Step 1. It starts at a noise source, usually some kind of vibrating physical object. Step 2. That noise is transmitted through a path, radiating through a medium like the air or the solid structure of a building. And Step 3. It arrives at the receiver, where it's finally perceived as a hazard. It's that simple. To successfully control noise, we just have to break this chain at one or more of these three links.
Ultimately, the severity of a noise problem is a function of two interacting variables: the raw strength of the noise source itself and the physical length of the separation path. Mathematically speaking, if we manipulate either the source's strength, say by substituting heavy machinery for a quieter alternative, or if we expand the physical distance to the receiver, we engineer a quieter environment.
Section 3. Controlling noise at source. Stopping it at origin.
Let's look at our first point of intervention. How can we modify the source to reduce its noise output before it even gets a chance to travel? Well, if the noise source is a machine, we've got some highly effective mechanical solutions. For large vibrating surfaces, we install dampers. These are amazing because they actually extract the raw vibration energy from the machine and dissipate it harmlessly as heat. Alternatively, we use vibration isolation. This stops the transmission of energy by introducing a flexible element, basically creating a physical break. Common isolators include heavy-duty springs, industrial rubber mounts, and cork. By floating a machine on these materials, we literally stop the noise right at its origin.
Section 4. Blocking the transmission path. Intercepting the wave.
Okay, but what if the sound energy successfully escapes the source? Our next engineering task is to intercept it, reduce its flow, or deflect it entirely before it crosses the path to the receiver. We have two primary path defenses here, and they operate on completely different principles. On one side, we have noise insulators. These act as solid, impenetrable barriers. They rely on high-density materials, think brick, thick glass, heavy concrete, or solid metal, to physically block the sound. On the other side, we have noise absorbers. Instead of acting like a wall, these act like a sponge. They use highly porous materials such as acoustical tiles, open-cell rubber foams, or melamine sponges to capture sound waves and literally convert that acoustic energy into microscopic heat inside the material itself. A truly well-engineered room is going to utilize a strategic mix of both.
Section 5. Defending the receiver. The final barrier. Sometimes source and path controls are technically impossible, or they're just not enough to bring the noise down to a safe level. When that happens, we have to alter the environment immediately surrounding the recipient. This is our final barrier of defense. For individuals in high-exposure areas, the most immediate step is personal protective equipment, earplugs, muffs, noise helmets, to heavily reduce occupational exposure. But defending the receiver goes beyond gear. It extends to the architecture around them. We're talking about rigorously sealing doors and windows against the outside and installing specific acoustic attenuators on all ventilation openings so that air can flow in, but sound absolutely cannot. Ultimately, it involves utilizing innovative building designs purposely structured to dramatically reduce the intrusion of external noise.
Section 6. Macro-level noise strategies.
urban planning.
Finally, let's zoom out from individual machines and single buildings. How does this framework apply to entire cities and populations? At the macro scale, civic leaders and urban planners apply this exact same engineering framework. They protect civilian receivers through strict zoning, isolating noisy industrial activities far away from residential areas. It requires long-term urban planning and robust public education. But it also involves biological acoustic barriers, specifically planting green belts of trees and thick shrubs along busy roads, hospitals, and schools to naturally absorb sound. And of course, it demands strict legislative measures, enforcing near-silent zones, banning pressure horns in automobiles, minimizing loudspeaker use, and framing dedicated noise pollution acts to actually give these rules some teeth.
As we wrap up this explainer, I really want you to take these academic principles out into the real world. Take a look at your own daily environment. Ask yourself, is your city actually using effective engineering controls like dampers and noise insulators right at the source? Or are they just relying on broad legislation and hoping that you, the receiver, can protect yourself? Understanding the source-path-receiver paradigm is the very first step in demanding and engineering a healthier, quieter world. Thanks so much for learning with me today.